We are going to continue our discussions of information processing over networks. Last time I talked about where the network converges to the solution, right? And I made several statements. In this lecture and in the next, and perhaps the one after that as well, we're going to establish many of these statements analytically. Okay, so the presentation may be a little bit demanding. You are going to see that the algebra, the arguments are not difficult, but you have to see it at least once so that you see the kind of arguments you need to follow to establish some of the properties I'm going to show you. Okay, so let's start. So this lecture starts part 5 of the course, and this is the part that's most demanding because that's where we establish the analytical properties of these networks. In particular, we establish stability and performance expressions as well. Okay? So this is part 5, and today's lecture is based on material from these two chapters, the end of chapter 8 and then the beginning of chapter 9. Okay, and the text is the one that I mentioned to you before. Okay? So let me first remind you of what we talked about last time, right? So last time I introduced a summary of the strategies that we are considering, for example, non-cooperative, consensus, and diffusion forms, right? Okay. So for example, in ATC diffusion, you have an adaptation step followed by a combination step. And in all of these implementations, you are using the approximate gradient vector because we are interested in stochastic approximation implementations. Fine. So these are the classes of algorithms we are interested in. And then last time I also explained there is a way to capture all these algorithms into a single description, right, by introducing 3 sets of combination coefficients, which I'm calling A1, A0, A2, right? If you put them into matrices, these matrices become left stochastic matrices, right? So you all remember that this description of the algorithm specializes to any one of the choices you have in the previous table by setting any 2 of these A's to the identity matrix, right? But of course, other options are also possible, and therefore this is a more general description. Okay. So if you collect the coefficients into matrices, these matrices will turn out to be left stochastic, right? Okay. And then I also introduced the product of the 3 matrices. Usually this would be just one of them because in general, 2 are the identity matrices, matrix. The other one is the A, like the consensus or diffusion. Okay. So P is in general A, but for generality, I introduced this notation P for the product of the 3 combination matrices, and it is this matrix that will require to be primitive, right? So that the network is strongly connected. If you look at P as a combination matrix itself, P will be left stochastic because if the A's are left stochastic, P will be left stochastic, easy to check. Okay, and if you look at it as a combination matrix, it should correspond to a strongly connected network. Okay, meaning any 2 agents will be connected by some path with positive weights, and there is at least one non-zero diagonal element in it, right? And we already know from the Perron-Frobenius theorem that if P is a primitive matrix corresponding to a strongly connected network, then it will have a single eigenvalue at 1, and the eigenvector that's associated with that eigenvalue, the right eigenvector, I'm going to call it P. I'm going to normalize its entries to add up to 1. And the Perron-Frobenius theorem ensures that all these entries are strictly positive, right? So P is my Perron eigenvector. In the case we are talking about consensus or diffusion strategies, this capital P is simply the A matrix, right? And P becomes the Perron eigenvector of the A matrix. Okay, and then we introduced a vector Q, which is a transformed version of P. If you remember, we simply take P, multiply it by A2, that's a vector, and then you scale all the entries of that product by the step sizes across the agents. In the particular case, for example, that we are talking about consensus or diffusion, we showed that A to P collapses to P. For example, when this is simply A, AP is P, right? When this is the identity, you also get P. So the Q's become simply scaled multiples of the P scaled by the step sizes, right? But this is for the more general case, you have the A2 there, and the entries of Q are positive. Okay? So these Q's, they depend on the topology of the P. Right? And why did we introduce the Q's? Because we showed last time, we argued, I stated, of course the proof will come today and next time, that the network will actually be converging in the mean square error sense. Okay? It will be converging to the minimizer of this weighted cost, weighted by the Q's. And this explained last time why this W star is called the Pareto solution, right? Okay. So it's not going to be omega 0, which is the minimizer of the unweighted version. It's going to be W star. Okay. So that's why we introduced the Q's, so that we have this cost function. And then I introduced this normalization of the step sizes, right? I can always express the step sizes in this form. Let mu max be the maximum step size, and every other step size is simply a scaled multiple of it, where these stars are numbers between 0 and 1. This is again what I said, right? If you minimize the unweighted cost, then it's unique minimizer because it's assumed to be bounded convex, satisfies this equation. The sum of the gradient vectors is 0, and the W star is such that the sum of the weighted gradient vectors is 0. And last time I stated that the network is going to converge in the mean square error sense to this W star, which we are going to prove today. Okay, so we are going to see that the argument requires some effort, but it is good. Right. So what did we do next? We introduced the error vectors because I would like to examine how the network evolves over time. So I define the errors relative to the W star. The error we are interested in is the first one, right? W relative to W star. The other two are intermediate errors, right? Intermediate error quantities. Okay. So I use the tilde notation for the errors. Okay. And these are measured relative to the Pareto solution. Right? We also defined the gradient noise vector, which is the difference between the actual gradient and the approximate gradient vector, right? This is what we are using. This is what you would like to use, right? We denoted it by S, okay? And of course, the gradient vector is, okay, the gradient vector is evaluated at, right? If you go back to the algorithm, right? You see the gradient vector is evaluated at this intermediate estimate here in this general formulation, okay? Very good. Now, there is one more thing that comes up in the network context, okay, which is this bias vector. I call it B sub k. Okay, this is the definition, and you'll see why it comes up. I'm defining it for now. The gradient noise you already know. Okay, this is the value of the gradient of the cost at omega star. Now, since you are dealing with the general case where the minimizers of the individual costs are not necessarily the same, they are not necessarily equal to omega star, so this gradient will not be 0. In the mean square error network case that we studied last time, all costs have the same minimizer, which agrees with the global minimizer, so this B doesn't come up. So this is one of the differences that will come up in the network context, okay, because okay, this gradient vector is not necessarily 0. So you will see in the derivation that it comes up. So I'm introducing it here, okay? So this is a vector, okay? Very good. And this is just an example, right? For the mean square error case, where the cost function is quadratic, right? The cost function in this case is quadratic, the expected value of dk, right? Minus uki omega squared. So for the quadratic cost, if you compute the difference between the true gradient and the approximate gradient based on the data, right? We have done this algebra a few times before. This is the expression for the gradient noise, right? I did it last time as well, okay? This is just an example to remind you that what it would look like in the quadratic case. But in this lecture, we'll be studying the more general case, okay? So this is just a simple example to refresh your memories, okay? Very good. So now, let's move on. This was a review of things we introduced last time, okay? So now let me do for the network what I did last time for the mean square error network. What did I do? I showed you how the error vector evolves over time. I derived a recursion for that so that you know how the dynamics of the network evolves over time. Let me do it again for the network, okay? For the general case where the JKs are not necessarily mean square error costs, okay? But like I said, in the general case, it will not be enough to work with the traditional errors. I have to extend them in dimension, and you will understand why. Okay, I have to extend them because the Hessian matrix now will not be block diagonal anymore. Okay, so this is one issue that will come up. Okay, so let me first define these things for you. Assume I have some generic vector omega. It's complex valued in general, right? The reason I need the extension is because I would like to deal with the general case of complex arguments as well, right? In signal processing and communications applications, it's not uncommon if you are designing a beamformer or if you are designing an equalizer that you deal with parameter vectors that are complex valued, right? So that's why in my presentations, I try to keep the presentation as general as possible. If you were only dealing with real data and real parameter vectors, these issues you will not observe, you will not see. You don't need to do the extension. But in the complex case, it's necessary. So define this omega, a vector. It has a real vector x and an imaginary vector y. The conjugate, right, will become a rho, right? That's the second line. X transpose minus j, y transpose. Now, if you transpose the conjugate, you are back to a vector, right? You are back to a vector. So if you compare the first line with the last line, this is almost like the traditional complex conjugation we do for scalars, right? You replace j by minus j. So that's what it does. That's what the succession of two operations, complex conjugation and standard transposition, will do for you, right? You just replace the j by minus j. Okay? So that's the notation, okay? So next, what I'm going to do, you're going to see that I need to determine recursion not just for the standard error, but also for this transformed version that I just introduced for these two. We need to study how these two vectors evolve over time together in the complex case, and not just the first one, as you are going to see. And this is what I just explained to you, right? What's the relation between this and this? This is a complex vector. You just replace the j by minus j. That's the relation, okay? So let's see. Okay. First of all, to find recursions for this transform vector from the original algorithm, all I did, I applied this transformation to all the entries, right? You see, I compute the conjugate transpose, right, on both sides. Here, conjugate transpose, right? And here, this was the gradient relative to omega star. So if you apply the conjugation and then the transposition, it becomes the gradient relative to omega transpose, right? So this is just writing down the recursions you saw before for these transform vectors. Now I can group them together, right? I can group them together. Here it is. So you see, I have recursions for the phi, and I have recursions for the, right, the transformed version of phi, right? So I put them together, one under the other. So now this is a vector of size 2n, just to the n, size 2n. So these are extended vectors, right? You see, so all the vectors got extended in this relation, right? And here I have the two gradient vectors, right? I just put them together. Of course, I don't want to carry this notation with me, so I'm introducing now a notation that will simplify all of this. But rather than writing, for example, all the time these two vectors one under the other, I'm just going to call it phi li extended. Okay, so before it used to be just phi li, but now it's extended, so twice as big in this way. Okay, each one of these, for example, this one will be called WKI extended. Okay, this is my notation. Okay, there it is. So these vectors now they are of size 2n by 1. That's all. They are extended, right? So I'm not introducing any new information. I'm only introducing these values. Okay? And likewise, I'm going to define the extended version of the Pareto solution, the extended version of the gradient noise, and the extended version of the bias factor. I will need these quantities, right? Okay. So you will see this E throughout Now, if I'm only dealing with real data and real vectors, you simply remove this E, right? You simply remove the E and you're working back with the original quantities, right? Okay? So this way the notation for both the complex case and the real case becomes relatively uniform. Okay? E has the complex case and without the E deals with the real case. So here it is. I rewrote the expression I had before using the extended notation, right? So the extended vector is the sum of the combination coefficients times the extended vector, right? I already am writing it for the errors, right? Remember, subtract W star from both sides. This becomes error here, and this becomes error here, right? I showed you last time. You understand this? Here, extended error, extended error, extended error, extended error. What did I do here? Here, I used to have, okay, here I used to have the approximate gradients, right? Now I replace them by the 2 gradient plus the gradient noise, because that was the definition of the gradient noise, right? Okay, very good. Now, are these recursions in the error vectors? Still, they are not exactly recursions in the error vectors. It is true, you see, from W tilde you go to phi tilde, you put phi tilde here, you go to psi tilde, from psi tilde to W tilde, but here you have an annoying term which depends on the estimate itself, not on the error, still, right? Okay. So up to here I didn't introduce anything, right? I just massaged the equations into this form. So now, if you remember, I'm going to apply the mean value theorem to this term. Remember, this is in one of the earlier lectures I showed you, right? I showed a form of the mean value theorem that will tell you, for example, that a function like this or a gradient vector like this, you can express it as the gradient vector at some other location plus a correction term, right? And that's a closed form expression for the difference between them, right? It's not your usual Taylor series where you have many terms and you have to cut some of them and approximate the expression. It is instead, right, a closed form representation for what each one of these is, right, at the location that you choose. So for example, this is what I'm going to do, right? I showed you this was one of the results we had earlier on. You see, equation, if you go to equation D20, appendix D, we showed this is a mean value theorem, right? Think of it as some sort of a Taylor series extension, right? But this is actually a closed form relation. So this is what I have, and I'm expressing them in terms of their values at the Pareto solution, right? So that, you see, that's how this bias vector comes up, because this is not zero anymore. Okay? In the mean square error case, you wouldn't have it. Okay? And the correction term will depend on the Haitian of the cost, which will be 2m by 2m by definition when you are dealing with complex arguments, right? So this is consistent with the fact that all our vectors now are 2m by 1. Right? So it will be an integral of the Haitian, which I'm just calling, right, the H at node K time I minus 1, right, times the error. So now I'm able to express that extended vector of gradient vectors here in terms of the error, right, in terms of the error. Understood? Okay. So I'm going to replace H phi tilde minus dKE into, right, this relation here. Okay. So when you do that, if here I'm just rewrote it. When you do that, okay, I'm just repeating the definitions from the previous page. Okay. Here it is. You see, this is what you get, right? Okay. The dKE plus that is that vector of gradients. Okay. So now I can group this term with that term, right? Now it becomes all errors, okay? Plus some driving terms, a bias term here and the gradient noise here. Fine so far? Okay. And like I explained last time, yes?
So what is random? What is...
Everything that's in both phases is random, right? That's my notation. So this H is random because it depends, look at the definition, right? The H is random because it depends on the error, right? All these intermediate errors are random, right? And H is random. The error is random. The noise is random. B is not random. Now, these equations tell me how the arrows are evolving at the individual nodes, right? I'm not interested in that. I'm interested in how the arrows are evolving across the network. So what did we do last time? We defined these vectors that collect all these arrows, in particular the W tilde, right? From node 1, node 2, node n to big W tilde, right? So I'm going to call it this big vector W tilde I extended. It will be the vector that will contain the individual W tilde. This is at node 1, right? Then node 2, and so forth, right? So what would be the size of this vector? 2m, and I have n of them. And you can do the same for this, the same for that, right? So when you do that, okay, before I get into that, I was explaining here the issue of h not being block diagonal. You see, this h here came from where? This h, let me make this remark because then this h is the integral of the Hessian matrix, right? Now, in the mean square arrow case, the Hessian matrix is quadratic, right? RU transpose. In general, it is, block diagonal, right? Block diagonal, okay? In general, it's not block diagonal, right? So this would be a 2m by 2m matrix. Now, if your h here will block diagonal, right? Will block diagonal, then you could only propagate the top parts of these vectors. Because this equation would be coupled. You understand? This equation would be coupled. Okay? You will only need, because this is block diagonal, so the top block multiplies the top part of this, right? So the top part of this decouples, right? So in that case, you don't need to define these extended vectors, even in the complex domain. If your h happens to be block diagonal, I don't need to extend these vectors W star transpose, right? It's because this is in general is not block diagonal that I needed this extension. You understand? So that's what I'm trying to explain in these slides here. That if it were block diagonal, then you don't need the extended version, right? Because you can just work with the top corner element. Understood? But we are going to continue to work with the general things. Okay? So here it is. I collect the arrow vectors from across my network, right? When all is said and done, you will get a neat expression. But to get there, I need to go through these details. Okay? I also collect the gradient vectors from across all the agents and the bias vectors from across all the agents. Okay. Here I'm just being more specific. So this is the extended vector across all the agents, and each one of them has this form, right? I'm just repeating the definition. Okay. So now, if you go back, this is what you're going to get. I need to introduce calligraphic aids, remember? I need to introduce the conical products. Last time I defined them and they were conical IN. Now it's conical I2M. Why? Because each block vector now has size 2M. That's the difference. Okay? So to capture both the real case and the imaginary case, you may see in the notes that I write instead IHM. When H is 1, that's the real case. When H is 2, that's the complex. So you introduce the extended combination matrices. Okay. Then the equations become simply this. Right? Just like last time for the mean-square arrow case. Right? This is the network arrow, network arrow, network arrow. These are the combination matrices. N is the block diagonal matrix containing the step sizes. Right? Just like the mean-square arrow case from last time, the difference you have I2M now other than IM. And H, this H is a block diagonal matrix containing the individual H's that we defined, right? Remember, each of these H's was an integral of a Hessian matrix. We don't know what it is, but we just know its form. Okay, and because these Hessian matrices will be bounded somehow, then we are going to use that to bound this matrix. Okay? And then this is the vector of all biases, and this is the vector of all gradient biases, right? Okay. So now I can take this phi tilde, which is A1 times that, put it here, and then take this phi tilde, put it there. I'll get the recursion only involving the W tilde. Okay. Here it is. So this is what I was aiming for. Right? So this derivation is to arrive at this recursion. From now on, we are going to work with this recursion. Okay. This tells you how the error vector across the network. So this W tilde I minus 1 is the state of the network at time I minus 1. E is because each one is extended to 2m plus 1. That's all. And then the A's are the same as before. The M is the same as before. Here you have the block H's. Okay. I don't know what they are exactly because they are the integral of the Hessian, which depends on the error, but I don't care. It's related to the Hessian. That's why I call it H. We are going to handle that. Okay. So how is this different from the mean square error case? In the mean square error case, I do not have the last term. Okay. And in the mean square error case, what was here? Constant, right? Because the Hessians in the quadratic case, they are all constants. R. You see? Now it's not a constant anymore, it's random. This is the constant. So in the general case, this adds a complication, right? The dynamics now here is less trivial than before. Before it was a constant matrix here. Okay, and then I could take expectations and make the comparisons I did last time between mean stability of consensus and diffusion and so forth. Now this is random now. Okay, so it's a little bit more involved, and that's why we will need to do the analysis that we are going to be doing today. Fine. So from now on, I'm going to work with this. You understand what the different terms here mean? Okay. Of course, the special case when all the A's are 1, this is the non-cooperative case. These A's will disappear essentially. That's all that will happen. That's what you have there. So this is the evolution of the network if the agents were working independently of each other. You get it as a special case. So this is a lemma summarizing the result. Okay. This is how the network error vector evolves over time in the general case. And then in the next slide, I'm just going to define, you see, I'm calling that matrix, this matrix here, this whole matrix here, B. Right? B. This is my notation. And it is random, both ways. And on the next slide, I'm telling you what the B is, what the A's are. I'm just reminding you. So this lemma simply summarizes what I have done so far. You see, the H is random because it depends on the errors, right? So we don't really know what this H is, but we are going to handle that, okay? And the calligraphic H is blocked out. Fine? So the conclusion so far is that I have a recursion that tells me how the error vector evolves over time. What I would like to show later on is that if I compute the variance of any one of these errors at any agent, let's say, agent K, that the limit soup of this, whether you do it in extended form or not extended form, it doesn't matter because the norms squared are related, right? So I want to show that this remains bounded for every agent. Actually, I will show that this is of the order of mu max. Even though, this is a time variant stochastic, right? This is a stochastic recursion, right? A stochastic recursion. Technically, it is nonlinear because this S depends on the weights. Remember, the gradient noise depends on phi, and phi is defined as a combination of W. So it depends on W. So I just rewrote it like that. So how do I show that a recursion like this actually leads to least first error stability, right? This is what we want to prove, okay? And we will be proving. What comes next is just an example. That, for example, in the quadratic case, H becomes block diagonal, and therefore the equation is simplifying what I did last time. That's all I'm telling you in this example. If you go to the recursions of the lemma, use the fact that the H now is a constant of block diagonal, the recursions I showed you become exactly what we did last time. And B, including B becomes 0. Right? Another example, what if everything is real? Omega is real, you don't have to extend. So here, in this example, I just repeat the derivation when everything is real. So I just work with the original recursions, I don't have to extend them, right? You start from these recursions, you get the error recursions, I don't have to extend them. Apply the mean value theorem to this, Right? Just repeat the same argument. Okay, this is the gradient noise. Introduce the errors. Apply the mean value theorem. Right? Okay. So you don't have any extended vectors anymore. And then when you put things together, you get a similar recursion to what I got in the complex case, but doesn't involve DE or SE or W tilde E. That's all. Fine. Okay. So this is the summary in the real case. I'm just writing it down. And in the real case, of course, the extended A's will be chronicle IM because now the vectors have subvectors of size n plus 1. Right? Very good so far? Okay, so I showed you how the error evolves. I haven't shown yet that it is stable, this will come. So now I would like to study how stable that recursion over the network is. And in a future lecture, what kind of convergence rate I can get and what kind of performance in steady state I can get. We're going to quantify all of this and derive expressions for all of this in terms of the network topology and in terms of the combination policies and so forth. Okay. To get there, I first need to remind you of the gradient noise model. We talked about this when we discussed single agent adaptation centralized solutions. So this is a reminder here. Okay. Remember, this is the definition of gradient noise at agent K. Difference between what you would like to use and what you end up using because you don't have the true gradient. Right? And this is simply a reminder of what the bias is. Okay. So I use this notation to denote the filtration that's determined by all previous weight vectors. Okay? This is essentially, I'm going to condition my expectations on F. And by that I mean I'm conditioning on all the past. That's all. Okay? This is just, will be a compact notation for me to say I'm computing the expected value of some variable condition on everything that happened up to time I minus 1. The technical term for it is filtration. Okay? So what are the assumptions we need to introduce on gradient noise? They are the same assumptions we introduced when we studied, for example, centralized solutions and also single agent solutions, right? And I showed you that many costs in practice, right, like quadratic costs, logistic costs, they satisfy these conditions, okay? I'm just reminding you what they are. That the gradient noise is 0. You would like the gradient noise to be 0. This means that you are using an approximation for the true gradient, right, that on average has the same value as the true gradient, okay? And that the noises are uncorrelated across the agents, and that they are circular across the agents, right? Second order circle. Remember when we studied centralized solutions, we introduced these assumptions, right? In the complex case, you need both, right? This is uncorrelatedness, this is circular, and that the variance condition, all conditioned on the past, and that the variance is bounded by phi squared. Right? These are exactly the same assumptions we introduced before. I'm just reminding you, right? And I showed you that several costs of interest automatically satisfy these conditions, right? Okay, very good. And I also mentioned further before that we can, this bound here, which is depends on the norm of phi squared, up to, I don't really care what these coefficients are. These are just coefficients, right? I can replace this phi by phi tilde and for some other coefficients I showed you before, right? That you can write the boundary in this form, or you can write it in this other form, okay, in this other form, for some other coefficients, but it involves the error instead of phi itself, right? Instead of involving the estimate, we can put the error here, right? We did the little algebra that showed you how that implies this. Okay? So for us, we are going to assume this, that it is zero mean, and the variance is bounded by the error, right? Of course, if you take expectation again, you remove the conditioning and then you introduce an E, right? Okay. We don't really care what these constants are, except to say that the variance of the error is indeed bounded. Okay? So this is for second order bounds, and then we also have the extension of this, right, to the fourth order case. That sometimes, as you are going to see later, we also need to assume that the fourth order moment of the noise is bounded, right? Not just the first, the second, but the fourth. And I also explained before, if the fourth order moment is bounded by this, it implies that the second order moment is bounded like that, right? We saw all of this before, so I'm just reminding you, right? And again, you can also use phi tilde here for some other constants instead, okay? So these are the conditions we had before on the gradient noise, okay? Which I'm going to be using today, okay? And this is just to show that if the fourth order bound holds, then the second order bound also holds, like we showed before, okay? So we did all of that. Good so far? Okay? So what I did so far, I started from the network, I derived the evolution of the weight error vector over the network, right? And I reminded you what are the conditions of the gradient noise process, because S appears in the recursion, right? Now we are going to examine the stability of the network, right? So what we want to show, what I would like to show, at least that's what I showed in chapter 9, this is where chapter 9 starts, is that the evolution of the error vectors across the network for any agent, right? They are bounded in this form, okay? For example, the mean square error will always be of the order of mu. Mu is very small, a very small step size. So this tells you that WKI gets close to W star within that range, okay? I'm going to show you also that the fourth order moment is bounded by the square of mu, okay? And that the mean error bounded by first order of mu, right? These are exactly the same results I proved for single agent adaptation. I proved for centralized solutions, right? The same thing I'm going to prove for the network, but the argument for the network is a little bit more involved. Why? Because you have a coupling among the agents, right? You have coupling now among the agents, but we are going to handle that, okay? So this is what we want to show. This is just another representation. So this is your Pareto solution. What we are saying, for example, let's take this. We are saying that for agent K, as I goes to infinity, it's going to enter a region, right, such that if you measure on average what the square distance is from omega star, if you measure this square distance on average, it will be of the order of mu, right? That's what we are saying, okay, in the limit. That you will enter a small region around omega star, and this will happen for every node. Okay. Of course, this requires proof, right? Okay. So I'm just reminding you of the definitions for the step size and the error, okay, of the global cost, the weighted cost, and the definition for Q, because I'm going to be using it improving the next statement of E, of the Perron eigenvector, and of the unweighted global. And now I'm going to prove the following result. Okay. Here I'm just reminding you of the equations, okay, because so what you have on top is the error equation, correct? That's how the error evolves over time. B is random. These are the A's, M depends on the step sizes, H depends on the H. What I would like to show is this theorem, that under the conditions I stated on the gradient noise, for example, zero conditionally zero mean and bounded second order moment, under these conditions, the fourth order moment I will need it later. For now, the second order moment is enough. Okay. That the algorithm is mean square stable. I want to show that if you leave this network running, that for small step sizes, there is a sufficiently small step size such that for any mu smaller than it, the algorithm will always be stable. Right? This is an important thing to show, because then you're showing that this network, right, will always remain stable regardless of the A1, A0, A2, as long as mu is very small. Okay. So let's prove. Okay, so this is the argument. The argument, I start by saying there is demanding, right? But you at least need to see this kind of argument at least once so that you get a feeling for it and understand why, okay, why we need to go through the arguments that we are doing, okay? So just follow. The argument is not difficult, but it is demanding. It involves several steps. So this is the error recursion, right? What do I want to do? I want to show that the mean square error, I'll just refer to it as the variance, okay, just to keep it. The variance of each W tilde k, right, is bounded by the order of mu. Right? I can focus, by the way, on the variance of this big W tilde r, right? If I look at this quantity here, so what is this quantity? Remember, this is a big vector which contains all the W tildes. So its square norm is the sum of the smaller square norms, right? So if it is of the order of mu, these smaller square norms are also of the order of mu. Okay. So now, if you were to evaluate the variance of this vector, by variance I mean the expected value of the norm of this vector squared, okay? So I'm just calling it variance, just as a short terminology. If you were to evaluate the variance of this, what would you do? Right? Just think with me. What would you do? Square it, right? W tilde multiply by W tilde starting the expectation, right? Okay. So on the right hand side, you have to multiply this by itself and take the expectation, right? So the first step that I'm doing, all of you would be doing. Okay? I'll tell you where we're going to divert. Okay? For now, it is trivial. Okay. But before it, I want you to do some notation that I forgot. But the first step will be exactly that. Let me introduce some notation, okay? This is B, right? This is B. What makes the argument challenging is that B has a random component, right? So I'm going to split the random components from B. You see, so the first part is simply the original P. Remember, the original P is the product of the A's. These are the calligraphic A's, so they will be the calligraphic P. The other part, I separated it, fine? So keep that for now. So that original P, I'm just showing you here. You see, each one of these A's is a canonical product. Using properties of canonical products, this calligraphic P is the canonical product of the original P with I. That's all, fine? This is just a small, okay, because this will be very useful. Okay, remember this one. Okay, this is the challenging part. Okay? Very good. The other thing I want to show you, remember that what was the vector Q? It was the matrix of mu's times A2 times P, right? This was the definition. So if I want to get any entry of Q, any particular entry of Q, just multiply from the left by the K basis vector, right? This is the vector that has all zeros except one. You would extract this, right? So if you multiply by EK here, you will extract mu K, right? Times the K flow of that. Correct? I'm just writing down what is the expression for the Kth entry of Q. Right? Why is it that I'm doing this? I'm just doing this to show you that the entries of Q are of the order of mu. They are of the order of mu. Because you see, P is a constant that contains constant numbers. A is a matrix, constant numbers. EK is the basis vector. So, right? And this mu K is simply tau time, right? The whole purpose of this is to show you that each Q is of the order of the step size, which is obvious because it's defined as the step size times constant values, right? Understand? Okay. Great. Another thing that we are going to need is, remember that P times P is P, where P is the Perron eigenvector, right? So if you extend it to the calligraphic P, this is the relation, right? Because what is this calligraphic P? It's P chronicle I times P chronicle I, right here. If you use properties of chronicle products, right, you get capital P times little p chronicle I, which gives you again this, right? So because of the properties of chronicle products, relation 16 is correct. Correct? I'm just writing them down. Here, M times A2 times P, that's the Q. But this is written in the chronicle product because this is a chronicle, right? This is the extended M, this is the extended A. So this will be the extended Q. Just use the properties of chronicle products. You will see, right, that this is that. And then remember, 1 transpose P is 1. So if you write it for 1 transpose chronicle I, P chronicle I, this is 1 chronicle I, which gives you I, right? So I just wrote these relations which we know in the extended domain because we will need it. Fine. The algebra so far is right. And remember, A1 transpose 1 is 1 because it's less stochastic. So for the extended cases, you get the same thing, right? Because this is A1 clonical I times the vector 1 clonical I, right? So do you all understand these relations on these pages? Okay. So nothing new so far. Okay, now here there is something new. Okay? This is where we diverge. Okay, one of the ones, right? So this P, right? You will see why we need this, okay? This P is primitive, right? This is the P, not the calligraphic P, right? Okay. Calligraphic always involves conical product. This is the notation. This P was assumed to be primitive because my network is strongly connected. What's so special about this strongly connected network or the primitive P? It has a single eigenvalue at 1. All the other eigenvalues less than 1. So I want to exploit that property. We need that property in this proof. What does it mean? If you introduce the Jordan decomposition of P, right, you will have a single eigenvalue sitting there at 1, and the rest you can collect them in Jordan blocks, right? We don't know what sizes they are, but these are Jordan blocks. You understand what the Jordan decomposition is, right? Now, you have seen a Jordan, so this Jordan decomposition looks like this. For example, you will have some eigenvalue on the diagonal and one below, for example, for a Jordan block of size 2, another, let's say, of size 3, correct? And so forth, right? And these lambdas will have magnitude less than 1. Okay? But here I'm introducing a variation of the Jordan decomposition. Okay? And the variation is I'm replacing the 1 by an epsilon that I'm free to choose. Okay? That's why I call it J sub epsilon. So let me explain to you on this next slide here. Take any matrix A. This is not the combination matrix. Any matrix A. Introduce its Jordan decomposition. Well, this is your traditional Jordan decomposition. T inverse, and J has eigenvalues with 1s on the lower diagonal, right? Now, introduce a diagonal matrix where epsilon is a small number you are free to choose, positive. 1 epsilon, right? I'm free to define this T. Now, I can come here and incorporate E inverse E, nothing changes, right? The T E inverse, I call it some T prime. Here you will have the inverse of that T prime. And here you will have some other J, right? If you check what this J will look like, multiplying by this diagonal E and its inverse, you will see all you do, you start from the original Jordan matrix and you replace the ones by epsilon. Okay, so this is an alternative way of representing your Jordan decomposition. Okay, you get a new Jordan decomposition, for A, let's say T prime, J epsilon, T prime inverse, where this J now will have epsilons on the lower diagonal. Okay, so if this is possible, that's possible. So I want to work with this decomposition. Okay, you'll understand why. Okay. So introduce the Jordan decomposition of P, the epsilon Jordan decomposition of P. The J will have this form. One will be sitting up there, right? Now, remember that the V epsilon and V epsilon inverse, they will contain the left eigenvectors and the right eigenvectors of, right? They are related to the left and right eigenvectors of P. For the eigenvalue at 1, right, I know that P times P is P, and 1 transpose P, right? So P is the right eigenvector. Okay, so that's why it appears, because you see this, you can write it as P V epsilon equals V epsilon J, right? So you can see the first column of VE, has to be an eigenvector corresponding to the eigenvalue at 1, correct? Are you following? Okay. P times the first vector of VE is the first vector of VE times 1. Okay, so that's why the first vector of VE is P. The rest I call it VR. I don't care what it is. And here also, you see, I could do V epsilon inverse P is J V epsilon inverse, right? From the same equation. Okay? So you can see that the first row of this has to be the an eigenvector whose eigenvalue is 1, right? And that's 1. So that's why the first row of the epsilon inverse is the vector 1. The rest I call it VL transpose. Just I put the T there just to be consistent that there is a T. Fine? Okay. So all I did here, because your matrix is strongly complex, P admits a Jordan decomposition of this form, where the J has a single entry at 1, all the others are strictly less than 1, and where the matrices P epsilon and the inverse of that, they start with P and 1. I don't care about the rest, but at least I know these facts. Correct? Okay. So far everything is moving smoothly, right? Okay. Here I'm just explaining to you what I mean by an epsilon Jordan block. Okay. Now, just because V epsilon inverse is identity, right? And you see V epsilon is PVR, and V epsilon inverse is the row vector 1 with VL underneath. If you multiply them together, you will get some equalities, right? Okay, so I'm just listing them here. Right? Fine? Understood? Very good. So now, I introduced the Jordan decomposition for P. What will be the Jordan decomposition for the calligraphic P? The Jordan decomposition for the calligraphic P, right, you simply extend V, extend J, extend V inverse. Because multiply them out, you will get P chronicle I, correct? You might say, why I'm doing all of this? You will understand, okay, very soon. I wrote the proof in this way, where I introduce everything first and then I go to the other. Now remember what was your B. Remember that your B, I wrote it as the difference of two things, right? Your calligraphic B minus, right? Minus the random part, okay? Just to go back. Here, calligraphic B minus A2 and HA1, right? Okay. So let's write it down here. Minus A2 and H A1. I think there is a transpose here. Anyway, maybe a transpose may be missing, but we'll figure it out. Correct? Okay, so you see, now I'm replacing P by its Jordan decomposition. Okay, here it is. Okay. Sorry, it is P transpose, right?
And A1 transpose.
And A1 transpose. Okay? So P transpose, you will transpose this product here, right? So you see, this comes first, times that, this is your P, correct? Minus something, okay, minus something. So you see, I defined a matrix here, and this matrix, the way I defined it, you are going to see on the next slide, it is the inverse of this first matrix, right? Let's call it the next inverse. This quantity, and then the inverse of this matrix, right? So if you write it like that, when I multiply this, which I'm calling X, by D, and then multiply it by this, you will be left with what you wanted, right? So, okay, here it is. So your D is the inverse of the first matrix, the inverse of the second matrix, right? What's the inverse of this matrix? The inverse here, property of chronicle products. You take the inverse of this, right? So that's my D. Fine so far? Okay. Now, this D is a big matrix, okay? I'm partitioning it into 2 by 2 block matrices, okay? 2 by 2 block matrices. This matrix here will be of size n by n, or 2m by 2m, okay? 2m by 2m because n. And then the size of the rest you will be able to figure it out, okay? Why I'm doing this? So all I'm doing now, I'm taking that matrix P, which controls the dynamics of the error, right? And I'm looking closely into its eigenstructure. This is what I'm doing. Okay, I'm looking closely because that matrix E has a constant part which is P and a random part. Okay, so I would like to look closely into the structure of that matrix E. So what I did, I rewrote this matrix E, okay, in terms of the Jordan decomposition of P, right? And in the middle, I have the difference of two matrices, right? So let's focus on this D now, because this D has the random component, okay? It's just a transformed version of that random component, transformed by the eigenvectors, fine? Okay. So if I look at this, okay, of course, this is a big matrix. I'm going to partition it and call the blocks 1, 1, 2, 1, 1, 2, 2, 2. The important thing, this block here is of size 2m by 2m. Okay? And then the rest is the rest. Okay? Now, I'm reminding you of the definitions here. Now, what's so special about these blocks? I'm going to show you now, this is the important thing, that these blocks, their entries are of the size of mu max. Each one of them. Each one of them. These are small matrices. Okay? Each one of these has entries of the size of mu, so they are small entries. Okay, this is what I want to show. Because remember now, each one of these has h in it. Of course, mu is here. You see, this is a constant, right? These are constant matrices. They depend on your p. This is a constant. A is a constant. A2 is a constant. M is mu, right? So okay, so it's not surprising to get mu here. The problem is this h. This h depends on the Hessian, which depends on the errors, right? But because this Hessian will be bounded in the sense I'm going to explain, because of that, these matrices are small matrices of the order of mu. And then I'm going to exploit this in the analysis. Okay? So this is what I'm going to show first, okay? Very good. So what are these matrices? For example, remember what V epsilon was? V epsilon was P, VR, right? I transpose. This is what this V epsilon is, okay? Chromical I, you will get P transpose chromical I, VR transpose chromical I. This is what this will be, okay? Now look, so for the first entry here, I'm only interested in pursuing this. P transpose chronicle I times A2 times M. What would that be? This would be Q transpose chronicle I, because this was one of the results I showed you before. Because remember, M A2P is Q by definition, right? This is just the extended version of that. And then V epsilon M, this here will be 1 VL. And then A1 transpose times 1, let's just look at the first column. That's 1 again. Okay. This is block diagonal. The block diagonal times 1, you get a column vector with H1, H2, H3, Hn, correct? So here you get these Q's, the entries of Q, multiplied by a block vector with values H1, H2, etc. So what do you get for D11? You end up finding that D11 is the sum of Q times H. Okay? I just computed explicitly what this is. You have to do these calculations. Okay? Write down what this is, write down what this is. Remember the definition of Q. Remember that A1 and A2 are left stochastic, that M is block diagonal, that H is block diagonal. Right? If you do this slowly for each one of them, you will get the expressions I have on the next slide. I'm not going to do the other three. This is just, okay. I would bore you if I do that, but just saw the first one, right? Why I'm writing the expressions? Because I want to show they are of the order of mu. Okay, and I'm reminding you here of the definition of H, correct so far? Okay. So let me show you first that this is of the order of mu, and then similar arguments you can apply to the other three. Okay. Very good. First of all, okay, remember that we assume early on that at least one function is strongly complex, so that the aggregate sum is strongly complex. This is our assumption, right? When we formulated the optimization problem, we said the aggregate cost is strongly complex, and that's meant if we assume that at least one of them is strongly complex. So I know that at least one cost, let's say of index k0, is strongly complex, which means its Hessian will be sufficiently away from 0, right? For some constants. Okay. So here I'm using the H, you see that, right? Okay. Very good. The other Hessian matrices, all I can say they are non-negative, right? Okay. So, because this matrix is an integral involving that, this matrix will be sufficiently away from 0. The others are non-negative. Fine? Okay. But here, you have a sum. These Q's are positive, right? One of these H's is sufficiently away from 0. The others are non-negative, right? So obviously, this D11 will be sufficiently away from 0. Okay? So this is, so here it is, right? So D11, okay, because it is a sum of Q times Hessians, it will be larger than or equal to one of them. Let's say the one of index k0, right? One of them. And I know that that one, okay, because the Q is of the order of mu, so then I know that D11 is larger than or equal to a quantity of the order of mu. Did you follow this argument? All the entries of D11, right? They are larger than or equal to some constant times I, and that constant is of the order of mu. So this matrix is larger than or equal to some multiple of mu times I. Fine? So this is from below, but it's also upper bounded now. I'm going to show you from above. Why? Because another assumption we introduced before is that the global cost is bounded from above. Sorry, the Hessian of the global cost is bounded from above. Right? Remember? We assume that Hessian. Yes. We assume that it is strongly convex, so that its Hessian is uniformly bounded from below. But then, another assumption that we introduce is that its Hessian is also uniformly bounded from above, that the gradient vector is Lipschitz, which means that it's uniformly bounded from above. Okay. So if the sum of, what's the Hessian of the global cost? It is the sum of the individual Hessians. And all these individual Hessian matrices are non-negative, right? If their sum is bounded from above, okay, and they are all non-negative, right, then each one of them is bounded from above by the same number, correct? If the sum is bounded from above and each one of them is non-negative, then each one of them is bounded from above. Okay? Well, if each one of them is bounded from above, and D11 is the sum of all of them multiplied by Q, D11 will also be bounded from above by the sum n times of this times the Q's, and each Q is of the order of mu, then D11 will also be bounded from above by a quantity of the order of mu. Are you following? Okay. So that's the algebra, right? So D11 will be bounded by n times that, and let's take the maximum Q, it doesn't matter, right? And therefore it's bounded from above. So D11 is bounded from above, is bounded from below by a quantity of the order of mu. So D11 itself is of the order of mu. And D11 is a Hermitian matrix. So its eigenvalues will be bounded from below and from above by a quantity of the order of mu. Okay. So here it is. So D11 is bounded from above, we showed you, and is bounded from below. I'm just being explicit now. Before I wrote of the order of u, now I wrote it explicitly what it was. Okay. Therefore, this D11 is bounded between some multiple of mu and some multiple of mu. This is O of mu, right? This is what we define the big O notation to be, which means that the eigenvalues are also bounded from above and from below. Okay. So now, this means, so what are the eigenvalues of I minus D? They will be of this form. 1 minus the eigenvalue of D, which is something of the order of mu, right? Okay. So, what's the conclusion of all of this? Even though H is a random matrix, I was able to conclude that the eigenvalues of this matrix, which will play an important role, they are of the form 1 minus some constant, I don't know what it is, but they are of this form, right, of this order. You understand? 1 minus something, so they are strictly less than 1. Okay, and that's why I introduced the Jordan decomposition you're going to see, so that original block, okay, the leftmost block, will have eigenvalues like this. Okay. Now, okay, similarly, all the other V's will have entries of the order of mu. Fine? Fine? Of course, here, another result. Since this is Hermitian, right, the two induced norm is the spectral radius, maximum eigenvalues. Since the eigenvalues are of this form, right, so obviously that norm is of this form, 1 minus something of. I don't really need to know what the constant is here. I just need to know that it is of this form, of this order, okay?
But here the underlying assumption of mu max is sufficiently small.
Sufficiently small, always. In all of our derivations, the step size is always assumed to be sufficiently small. Okay? It's a positive number, sufficiently small. Okay? Now here, I'm not going to go through this derivation because it's not difficult to show that all the others are also of the order of mu. Okay, it's very, very simple. If you go, let's say, to this expression here, you want to show that it is also of the order of mu. You have mu here, and this also is bounded from above and from below, of course, using similar arguments, right? So you can pursue this. I have the slides here, and it is in your notes. You see the norm of this. I just wrote down the expression, okay, upper, and then the norm of this block diagonal matrix, right? Upper bounded by the maximum individual norm which are bounded, right? So you get here all quantities that are bounded, and this too is of the order of mu. So that if you just repeat the argument, here I'm just being explicit, okay? But what's important to us is that everything else here is a constant. Mu appears only inside Q, so the final answer here will be of the order of mu. Okay? Fine? Fine? Okay? So this is, by the way, so what is the two induced norm of a chronicle product? If I have A chronicle B, what are the eigenvalues of A chronicle B? The pairwise products of eigenvalues. What about the singular values? Similar result. Okay? So the singular values here, right, would be the product of the singular values 1 times the norm of 2. So that's why it gets here norm of 2. Okay? And so this is trivial, you can't do it. I'm not going to do it for everything. Okay? I'm not going to do it for everything. Fine. But the important thing, rather than write that the norms are of the order of mu, because all I'm doing is saying that it's some constant times mu. Because in my expressions later, I'm going to use this form rather than that form, and I call the constants accordingly: 1, 2 for 1, 2, 2, 2 for 2, 2, and so forth. I don't know what these forms. I don't care what they are, but they exist and they are finite. Okay.
What if these constants are very big?
Sorry?
Can these constants be very big?
Yeah, the constant can be very big, but remember, mu is always very small. Right? It can be as small as you need it to be. Okay? The important thing is that these norms, remember when I defined the notation of the order of something, when I say that, let's say, x is of the order of mu, it means it's bounded by some constant times mu. That constant can be large. Okay? Can be large. But x changes proportionally with mu. That's the important thing. X changes proportionally with mu. Okay? So these constants can be large. In the derivation I just showed you, okay, if you follow it, you know exactly what the constant is. It is related to these other quantities. You know exactly what it is. Okay? So, very good. Okay. So now, I'm reminding you of the definition of B, right? Remember that I wrote it in this form. I took out the eigenvectors on this side, on that side, okay? And this quantity D in the middle, I partitioned it into 4 quantities like this. That I'm just reminding you, okay? I'm going to, so rather than write this all the time, okay, so here you see, I'm going to introduce this notation. J epsilon chronicle I is the calligraphic J, and V chronicle I is the calligraphic. So here we have V chronicle I, V inverse chronicle I. So I'm going to use the calligraphic V for this, calligraphic V inverse for that. Okay, just to keep it simple. Okay. So here it is, you see. Okay. Now, what do you get in the middle? Let's look at the middle, and this is important. You see, what is this J chronicle I? Remember that the J is 1, J epsilon, right? Chronicle I, right? This will be 1 chronicle I, that's I, and then the calligraphic J, right? Minus D. So you see, when I compute this minus D, what will you get? You will get I minus D11, minus D21, minus D12, and J epsilon minus D22, right? Here it is. Fine. Okay. So what's the conclusion so far? All the arguments I have used so far was to arrive at this point to show you that this matrix B, which determines the dynamics of your network, can be partitioned because see, this is a similarity transformation, right? I don't really care what they are. It's a similarity transformation. There are some constant matrices, right? So B is similar to this matrix in the middle. The off-diagonal entries are small, of the order of mu, right? The 1-1 block entry has stable eigenvalues, right? I mean, all the eigenvalues are strictly less than 1 in magnitude. But they are all of the form 1 minus some sigma times mu max. Okay. Here, all the eigenvalues of this are inside the unit circle minus a small number of the order of mu. So now I'm going to exploit these properties. Okay. So all I have done so far was exploit the fact that your network is strongly connected to show you that the dynamics of the network, right, the B matrix has this structure. Okay, has this structure. And the strong connectedness was used to get this form here, because this came from the 1, right? That I had that eigenvalue alone, 1, right? Okay. Very good. So now let's put this to work. Okay, let's put this to work. Like I said before, let's go back to the weight error recursion. Here, W tilde, W. This is the weight error recursion. What did I do here? Okay. I want to use a transformed version of it. Okay. I just want to use this center matrix here because B is similar to it, right? So look what I do. I put V and V inverse here, nothing changed, right? And I multiply from the left by V transpose. So you get V transpose here, V transpose here, V transpose here, nothing changed. This is the same equation. I'm just doing a change of variables, okay? But the important thing is that now this, I can replace it by this, correct? This, I can just call it some vector, right? That is the same vector at time I minus 1, right? This is just a change of variables. So let's look at this. So here it is, you see. So this quantity here, remember that V epsilon transpose is P VR transpose. So here it is. So V epsilon times W tilde, right, will contain 2 parts, right? The P and the VR, right? Times the W tilde. Fine. So I'm just calling these 2 parts, so I can partition it into 2 parts, into W bar and W j. What's the size of W bar? 2m by 1. 2m by 1, right? And the rest will be 2mn minus 1, very basic. Look at W bar E. What is the expression for W bar E? If you compute this, it's a weighted sum of the errors across the network, right? Weighted by the P's, correct? Because you see, this is a row vector here, contains P1, P2, P3, right? Times the W tilde. So this W bar E is telling you how the weighted sum of the weight error vectors across the network is involved. W check is something else. The performance will very much depend on that, on the first W bar, as you're going to see. The second term that appears in the recursion, I also partitioned it into two parts. The top part S bar, the bottom part S check. The bar quantity is the smaller quantity always. The rest I call them check. Now here, again, the last term, okay, the last term here contains the bias. Again, I partition it into two. But the top part is 0 because of the definition of B. Let's look at that. And this is important. Why is the top part 0? You see, P transpose conical I times A2 transpose times N. What's that? That's the vector Q. That's the definition of Q. So you get Q transpose times A times the vector BE. Right? What is the vector BE? It contains all the gradient vectors. So when you multiply by this is the sum of the weighted Q's of the weighted gradient vectors weighted by Q. Correct? And what's that? By definition it is 0. Right? Because the W star. So that's how we identified that this is the W star where the network is going to converge to, because it comes from this. Okay. Did you understand that this is 0? Did you understand?
No, just what was the the
definition of B? B, remember B is the bias, right? The B factor at node K is the gradient at node K at W star, right? BE, you would extend it. But let's just work with B, just to convey the idea, right? When you multiply Q, so this B contains all these W's, all these gradient vectors, one underneath the other, right? Multiply them by the vector of Q's, you will get a sum, a weighted sum of the gradient vectors, which by definition is 0. So that's why I get 0 under the bar. And the rest I call it B check. Fine so far? Now this B check, you see, these are constants, constant, the n is of the order of mu. These are gradients at W star, they are bounded constant. So this B check is of the order of mu as well, right? It's useful to know that the entries of this vector is of the order of mu. Fine? So here I'm showing that it is 0. And that that's of the order of mu. Okay? Fine. So now I come back to what you would do if I were to ask you to solve this problem. After I give you this big hint, right? This big hint, work with this transformed state space. This is a state space recursion, right? Fine. You see, this is the vector that was transformed, which I partitioned into bar and check. Bar and check. Bar and check. 0 and check. Correct? And this is the 2 by 2 matrix. So all I did, right, so far is just start from the weight error recursion for the network, take the B matrix, transform it, right? Transform it with what transformation? The one that comes from the Jordan decomposition of P. Right? That's all I did, right? Introduce the vectors, right, that come from the Jordan, the V matrix, right, V epsilon, and apply it to your weight error recursion. If you do that, your recursion becomes of this form. Correct? Okay. So now why is this form convenient? This is what you're going to see for the rest of the lecture, right? So now let's continue with this. Right? Yeah?
Okay, so why is it that you identified that a network is going to converge to W star being referred to optimum solution?
Yes.
Is it just for convenience so that you can set the B bar to 0?
When I continue the argument, you will see why that's important. Okay? Why that's necessary. Okay. Let me continue the argument. For now, because of the definition of W star, we know that that should be 0. Okay. Now, so just write down the recursion for the W bar, here it is. For the W check, here it is. Right? I just wrote them separately. Okay? Of course, they are coupled, right? W bar, W check, W bar. Okay? Now, what I'm going to show I want to evaluate the variances of these two recursions. Now the arguments become more standard, okay? To evaluate the variance of this, assume I gave you this recursion and I asked to show that the variance of that is of the order of mu. Okay, so what would you do? You would come to this, square it, and take expectation, right? Square this and take expectation. Okay. Now, if you were to do it the conventional way, to square this and take expectations, what would happen? You'll get the square of this, the square of this, the square of this, and cross terms, correct? Okay. Cross terms with S would be 0 to handle. They will disappear under expectation because S is 0 mean. But you'll get into trouble because of this cross term here, which we don't know how to evaluate that. So that's not what we are going to do. Right? Okay. So what's the alternative?
Yes.
Sorry, Jensen's inequality. Remember I explained this to you before, to avoid this cross-coupling. That's why we go to the Jensen's inequality, right? Okay, so let's look at that. And then a similar argument I will do here. You know, the arguments now are very parallel. Okay, so let's do that quickly. Okay, so here it is. You see, all I did, I squared. Okay, so what I did, when you square this and you take expectation, I will treat these two together separately from that, and then the expectation will disappear, right? The cross term will disappear. If I treat this as a quantity that I'm multiplying by S under expectation, it disappears, but keep this together. Fine so far? Okay? So here it is, you see? So this term, and because this is conditional, of course, you don't have expectation here. Okay. Fine. So you all understand where this came from? And I did the same thing for the second equation. I kept everything together squared and the error term separate, right? Fine. Now, if you take expectation again, you remove the condition, right? Okay. So remove the conditioning, put expectation here, and remove the condition, right? Okay. So that's what we do next. So far I have these equations. Okay. Now I don't want to expand this expectation because I'll get a cross term, right? So what I'm going to do here, I'll do something similar. This is Jensen's inequality. Let's look at it. It's not difficult, but you need to see it. I have to apply Jensen's inequality here. Okay, what does Jensen's inequality say? This is the stochastic version of Jensen's inequality, right? You see, T is a variable I am free to choose. Okay. So I'm going to multiply here by 1 minus T times 1 over T, and T times 1 over T. I did not change anything, right? Okay. However, I have 1 minus T here and T here. So I have a convex combination of two things, right? Convex combination of two things. Okay. Therefore, the expected value, right, of the square of that from Jensen's inequality, right, will be upper bounded by the convex combination, you see, T1 minus T of the individual quadratics. Correct? That's what Jensen's inequality tells you, because this is a convex function, right? Okay, are you following? Fine. Very good. Now, because of the quadratic, 1 minus T comes out as 1 minus T squared. And you have 1 minus T here, it cancels, right? The 1 over T squared comes out, you get 1 over T. So far, so good. Okay? But now, the norm of the product is upper bounded by the product of the norms. Right? So far, so good. Product of the norms. But I know, I just showed you that what is this norm? It's upper bounded by something of this form. Right? What is this norm? It's upper bounded by something of this form. Right? That's what I showed you before, right? Of the order of mu. I am free to choose T. And it needs to be a positive number less than 1 because it has to give the convex combination coefficients. So let me choose T to be sigma 1 mu max. Then it cancels one of these, right? And then here you get sigma 1 mu max. One of these mu cancels, right? Okay. So when you do that, you get this. So from that recursion, and this is where the strong convexity was used, and this is why I partitioned D in that form, so that I end up here with a driving term that is strictly less than 1. The dynamics is driven by this coefficient that is strictly less than 1. So this variance is a number less than 1, that variance, and this is the cross coupling gives me right between these two variables, right? And that's very good. Now I can do the same thing for the second recursion. Let's do the same thing for the second recursion, for the check, okay? The same thing for the second recursion. I just noted that's the first line here. So now I introduced T1 over T, 1 minus T, 1 minus T. Fine? Same argument. Again, I already skipped the line here, right? This will give me 1 over T here. This will give me 1 over 1 minus T. Fine, so far? Okay. So let's find out what is this and what is this. Okay. So let's look at the first one here. So this is J times W norm squared. Okay. So J times W norm squared, just write it down, right? So it is the vector times J and then times its transpose, right? The vector times its transpose. That's what the norm squared is. I can group the J's together, right? But this is exactly a vector times some matrix times the vector transpose. And that is a Hermitian matrix. What you have here. Now remember radius, right? We mentioned this before. Okay, for a Hermitian matrix, this quadratics like this are upper bounded by the maximum eigenvalue, the smallest eigenvalue. Correct? So this quantity is upper bounded by the spectral radius of this times the norm of W check. What is that spectral radius? Let's find it. Okay. What is the spectral radius of JJ star? What is J? It has Jordan blocks, right? So let's take a Jordan block multiplied by the transpose and see what's the spectral radius. Okay. So here it is. So this is J chronicle I, J chronicle I. This is just to show you that I have to look at the spectral radius of the J times J star. So let's take a Jordan block, multiply by its transpose, you get this. Now remember, the spectral radius of any matrix is upper bounded by any norm of the matrix. Let's take the one norm, called maximum column sum, right? So the spectral radius of this is upper bounded by the maximum column sum. What is the maximum column sum? Epsilon lambda plus this plus epsilon lambda star, right? This is only for one Jordan block, but that matrix may have many Jordan blocks, right? Okay. So here it is. So this is upper bounded by this sum, which is actually nothing but this square. This is squared. But because you have many Jordan blocks, then the spectral radius of this product is the maximum that this can be over the Jordan blocks. Well, the maximum the lambda can be over the Jordan blocks is the spectral radius of that Jordan block. So what this result is showing is that the spectral radius that I'm interested in is actually upper bounded by the spectral radius of J itself, plus an epsilon. And this now, you see why we chose epsilon and didn't keep it at 1. Because had you kept it at 1, this result would be larger than 1. It can be larger than 1, right? Depending on, well, in general, it would be larger than. But because epsilon, you are free to choose epsilon, and because this is a stable matrix, we can always choose this epsilon to keep this stable, less than 1. Understand now why we introduced the epsilon? Because of this conclusion. Okay, so very good. So far, I showed that first, right, if you go back, we showed that this here is upper bounded by the spectral radius of this times the norm of that region. Fine? Okay, let's look at the second term, okay, and then we'll put things together and get a conclusion out of this. Okay. let's look at this. What is the bound for that? Here, use Jensen's inequality. You see? Again. Okay, so here I'm saying let's choose T to be rho plus epsilon so that it cancels one of these. Okay? So then you will get here rho plus epsilon only, and then here 1 minus that, which is this. So let's look at that. If you look at that, how do I bound it? Well, I'm going to use Jensen's inequality. Multiply by 3, 1 over 3, 3, 1 over 3, 3, 1 over 3. Did I change anything? I did not change anything. Right? I told you about this thing before. But this is a convex combination. I can bring the one out, right? And then this 3 comes out as a line. So that's why it becomes 3. And each one of these terms, I know that this is bounded, you know. This is bounded, right? Right? So I get that bound. So if you put things together, okay, here it is. So now let's group all of these things together. What's left, by the way? So what's left? I found a recursion for the variance of the check in terms of the check and the W bar, but I still need this quantity. And in the previous case, let me go back there. Also, I still need this quantity. Remember, S bar and S check, they were transformed vectors of S. I need bounds on these. But you see, bounds on these, I have them in the notes, but that was the assumption of the gradient noise. Didn't we assume that the gradient noise, the variance of the gradient noise is bounded by the variance of the error vectors? These are transformed versions of these gradient noise vectors. So similarly, they will have bounds on them. And these will be bounds in terms of these quantities. So when I compute these bounds and put them here, I will end up with a recursion that will only involve the W check and W bar, and the other one will involve the W check and W bar, and the S bar and the S check will disappear. You understand? This is where the argument is going, okay? So doing that quickly. So here it is. I need to bound each one. Rather than bound each one, I'm going to bound the sum. And that bound is a bound for each one. Why do I bound the sum? Because the sum is the expected value of the two vectors together. But these two vectors together, S bar, S check, came from the definition of S, right? So this is upper bounded by the norm of S. But remember, the norm of S squared is the sum of the individual gradient noises, right? The norm is squared of the individual gradient noises, right? And each one of them is bounded. So something here, mu squared times that. Fine so far? Okay, so let's look at this. Here it is. So this norm squared is the sum of the individual norms extended. Well, it is 2 times the individual norm because, right? Okay. And then the individual norm, remember that it was bounded by the norm of the error, right? But phi tilde was the sum of the W tildes. Very good. Here I can use Jensen's inequality because this is a convex function of a convex combination. So I can take the A out. And then I can replace the A by 1 because they are all less than or equal to 1. So this is upper bounded by that. So you see that I end up getting a bound for the gradient noise in terms of the errors that, right? That are in the equations, because the W bar and the W check, they are simply scale multiples of these errors. Okay? So this is just some algebra. Here it is, right? So this is the sum, so there is something missing here. The sum over all over here. This is the sum of over these errors, which is the sum of all of the errors, right? The norm squared. And then this W tilde, V inverse V, the same thing, nothing changed. But the reason I do that is because this becomes the transformed vector that I defined before. And then I related the bounds of the gradient noise to the original variances. You understand, I did not do this algebra in great detail, it's just algebra, okay? But you understand where this comes from. I can bound the variance of the gradient noise in terms of the variances of the W bar, W check. Okay? So if you take this and you plug it back, okay, so here it is, the variance will be bounded. So if you take this and you plug it back, okay, so you will end up with the form. Okay, so here it is, when I plug it back, you see you get additional terms. Okay, don't worry much about the algebra, follow the idea now. Okay, so what's this? And here I put it for double check, here it is for double bar, here for double check. Okay, when all is said and done, this is what you get. Forget about these expressions. Okay? This is what you get when all is said and done. Okay? This is what you get. This is a neater expression. I wanted to show you that one so that you will laugh. Okay, this is the ultimate result. This is what we proved. We proved that the dynamics of the network evolves according to this inequality recursion. This is element-wise inequality. Where I know the size of each one of these. I don't care the exact expression, the size. For example, A is 1 minus 4 mu, B is 4 mu, C is 4 mu squared, and D is this. And E and E plus F also, if you look back, E and E plus F, E is 4 mu squared, F is 4 mu squared, so this here is 1 mu squared. That's what matters to us, okay? Now, let's look at this. Is this a stable evolution? This is a constant matrix. Okay. Well, what is the spectral radius? The spectral radius of gamma is bounded by its one norm, right? The one norm, this plus that, this plus that, could be this or that, right? Now, because the mu is small, mu squared is smaller. So the one norm of this column here is always strictly less than 1. What about the one norm of this? Well, you are free to choose epsilon, the epsilon comes up again, and you are free to choose mu. You can always choose them to make this sum less than 1. So gamma is always guaranteed to be strictly less than 1. You understand? You also understand why this epsilon was necessary, right? You would have been stuck here. Okay? Fine. So this gamma is stable. So if you iterate this, where will that recursion go to? Right? It will go to I minus gamma inverse times this. Correct? The limit of this, or lim sup of that, will be I minus gamma inverse times that. Okay? So this is the argument about this. Okay. So what is I minus gamma inverse? Well, the inverse of this is a 2 by 2 matrix. I know the size of A, B, C, D, then you will find out that the size of I minus gamma inverse is like this. For example, take any element. Okay, B divided by this, you will find out that this is of the order of 1, of the order of 1, of the order of mu, of the order of 1 over mu. Okay. But this is being multiplied by what? Will be multiplied by the order of mu squared, right? So multiply it by the order of mu squared here. What will you get? 1 over mu times mu squared plus mu squared is of the order of mu. Mu times mu squared plus mu squared is of the order of mu squared, right? So you conclude that these two vectors are of the order of mu and mu squared, right? But remember that these vectors, they are related to the original W, right? Let's go back. The original W that I'm interested in is the transformed version of these vectors, right? So you can take the norm of this out, I'm just calling it V2, and then the norm, the sum of these two. This is mu, this is mu squared. That's how you get mu. You are done, right? You follow the argument? I told you, I warned you, yeah, last time and today, right? That is demanding, okay? So it was not for lack of warning, but it's actually a very interesting, it's not a trivial argument to show that these networks work. That's what I always tell you. Deriving an algorithm, an adaptive algorithm, is easy. But showing that it works is not trivial. Okay? That's why I always recommend don't use the title a new adaptive algorithm or a new this or a new that. The challenging part is not in the novelty of the algorithm. The challenging part is in showing that the algorithm works, as you see in this lecture. This lecture is a prime example of that. Okay? Did you follow? I know you don't remember everything. Okay, but you have to understand all these arguments were to show I have randomness in my network. I have randomness. Okay, but I have some bounds on the costs, on the variations of the costs. So how can I exploit that to conclude that this network actually is going to function properly despite the coupling that I have among the agents? So the way to do that is to pick a convenient transformation that decouples the system into these two parts. Okay? When you decouple the system into these two parts, you get a matrix here that is stable, provably stable. Right? Because you can choose epsilon, you can choose u very small to make it stable. Therefore, this will evolve to the order of t. Understand? Okay. Now, of course, I'm not going to do all of this again for the fourth order moment. Okay. Because I know you will be mad at me. Okay. But I know you are also smart, you can follow the derivation. So this is what I'm going to do. Okay. So we proved mean square error convergence. Okay? That it gets there. So in the future lecture, we want to know how close it gets there. That's performance. Okay? So that's coming later. To get to the performance analysis, I'm not only interested in telling you that it's getting there, but I'm also interested in telling you how close it gets to that star. To get there, I will need to show that the network is also stable, that the error vector is also, the fourth order moment of the error vector is also stable. Okay? So, I'll just tell you what the result is because the arguments are very similar. Okay? The arguments are very similar, more tedious, but very similar because this is our fourth order moment. Okay? So, rather than applying Jensen's inequality to the expected value of norm squared, you have to apply Jensen's inequality to the expected value of norm to the fourth. Right? You have to use arguments like that, okay? So the arguments are very similar in nature. Now, given what I did here, you can follow it on your own, okay? So I'm not going to go through that argument in detail, but it is in the notes, okay? So this is what we want to show now. We want to show that the algorithm is stable from the fourth order moment perspective. The fourth order moment is converges to this region, okay? How would you do it? You would write down the error recursion, you would transform it. Right now you know what the transformation is, and you understand why that transformation. Transform it, then compute fourth order moments, right? Use Jensen's inequalities a few times, right? The argument, the main elements of the argument are very similar. They are done in the notes, okay? Just follow them. When you follow the arguments, this is what you get. Okay? So the fourth order moments, okay? Very similar relation. You get it. Okay? The same gamma. Okay. Here it is. Dragging term of this order. But you get this additional term because when you have these fourth order moments, products of second order moments will also appear and they will give rise to an additional term. But that doesn't bother us because I just showed you how big these things are. I just showed you that in the limit this goes to mu squared, right? This is second order moment, right? So if you repeat the similar arguments, you will arrive at this recursion here, that the fourth order moment vectors evolve according to this recursion. Okay, very good. So this is stable. Therefore, the lim sup of this in the limit is going to go to I minus gamma inverse times this. Correct? And here I'm showing you what I'll decide. I didn't show you the expressions, because then you would laugh again. Right? Okay, I just showed you the sizes. Okay? Here, the sizes. That's what's important. The expressions are not important. Okay? And here, the sizes. Okay? So I minus gamma inverse times the sum of this plus that, right? Okay. You see, this times that would be what? Mu squared times mu plus mu cubed times mu squared, that would be mu cubed. Mu to the fourth times mu, that plus mu squared times mu squared, that would be mu to the fourth, right? plus mu to the fourth times mu to the fourth. Okay, so that would be this. Times I minus gamma inverse times this. So what you get? Okay, you will get mu squared and mu to the fourth, right? Okay. There it is. Right? Okay. So this is for this, but now I know how this relates to the original vector, just like before. You see, the original arrow vector is a transformed version of the W check W bar. That's how we defined it originally, right? So I take this norm out, okay? Just some constants here, okay? And then this quantity here, using Jensen's inequality, will be bounded by this, and we already know this is mu squared, this is mu to the fourth, and you get mu squared. You understand? Okay? This is a sketch of the proof, right? If you are interested in the proof, here it is. You can follow it, right? You see, I start from the same recursions. I'm not go through it, I just would like to see. You start from the same recursion, now take the fourth order moment, right? Because that's what I did. I wrote the square is the square of this, the square of that, under expectation, right? If you take the fourth order power here, and you use a certain inequality here that I have for the fourth order power. So if you follow these arguments, you will end up with something like this, okay, for example, for the bar quantity. And then you see here, again, same thing, Jensen's inequality to bounded. Okay. And then for the check quantity, we do the same thing. Okay. Again, Jensen's inequality to bounded. Okay. Again, the bound of flow. And then when you put things together, bounds on the arrow. I'm getting there. I'm showing you that the proof is there. I just want to convince you that this is not out of nowhere. The proof is there. Here it is. I have added the same expression, right? So the proof is in the notes, it is in the slides, okay? So this is what I did today. So what I did today, I know this was a demanding lecture, but you need to see that this is not trivial, okay? It is not trivial, but it is doable. Okay, I showed that the distributed strategies that we introduced a few lectures ago, if you run them over a strongly connected network, and if you assume that the gradient noise has bounded second order moment or bounded fourth order moment, then these algorithms will be stable. Right? The second order moment of the weight error vector will be of the order of mu, right? And the fourth order moment will be of the order of u squared, right? So there is one thing that's left. Which one? First order. That will take the next lecture. Okay, the first moment, and I will explain it next time. Okay, but that's the kind of arguments you need to show that these algorithms are stable. Right? Good. Okay, so I'm going to stop.